So previously we had seen that the Maxwell equations give rise to light being a transverse electromagnetic wave like what you're seeing here. You see that the electric and magnetic fields are perpendicular to each other, and the direction of propagation is in the direction of E cross B, which is known as the Poynting vector. I've gone ahead and marked the electric field at this exact location right here, just so that we can more readily focus on what's happening with the electric field. So this kind of a light wave is what is called a linearly polarized light wave. There is a variant called circular polarization, but that's beyond the scope of our treatment here. Now, the hallmark of this is that we are noticing that the electric field is varying in the vertical plane. So we would say here that the light is vertically polarized. And the reason for this, again, is that because virtually every detector for light, except for a handful of super specialized detectors, is only really sensitive to the electric field and doesn't pay any attention to the magnetic field. So when we think about polarization of light, it's natural to think about the electric field. So this would be an example of it being horizontally polarized. This here would be vertically polarized. This here would be an example of horizontal polarization. And you can have anything in between that your little heart desires. So here, for instance, we would be polarized at about a 45-degree angle. Now, since the waving is happening happening in both directions, we just refer to the polarization. There's a 180-degree ambiguity in the polarization axis. So we could either say this is oscillating at 0 degrees or 180. Most people probably call it 0 and tend to keep the angles between 0 and 180. All right, so how can we make light that's like this, and how can we detect light that's like this? Well, it turns out that with most light sources, but not all, the light comes out unpolarized. What that means is that light coming off from different atoms from the light source will be pointing in different random polarization directions. So I'm going to attempt to schematically indicate that if this is our transmission axis here, I'm just going to schematically indicate that by showing electric fields that are oscillating in every which way in comparison. These are all coming from slightly different sources, and also it turns out that every few nanoseconds or so from any particular atom, the direction of polarization shifts, so it's a big mess. So the way that you can make light be polarized is you can use a polarizing medium. That's one way you can do it. So if you've ever seen like a sheet of Polaroid or something like that, and that will be coming up in a demo real quick here. If I have a sheet of polarizing material here, what's happening is within the polarizing material is a bunch of long chain polymers that have been doped so that they have a good mobility in the valence band across the polymer. So what this is doing is this is acting like a zillion little antennas all placed together. So any component of electric field that is oriented vertically in this example here will cause the electrons to slosh back and forth in here. But the energy to make the electron slosh had to come from somewhere, and that came from that component of the electric field. On the other hand, side to side, it's too skinny to get any effective sloshing action happening. And so what gets passed through is what didn't get absorbed. In this case, just the horizontal bit of it. Now, because we're more interested in the effect rather than the cause, we don't focus on the absorption, we focus on what gets transmitted. We say that this direction corresponds to the polarization axis of the material. Now, this isn't the only way that this can be done. There are certain classes of materials, such as calcite, that have a property called Birefringence. And what that means is that the light will bend at different angles depending on the polarization, and this is due to the crystal structure. So you can see that in this video clip right here. So what you're seeing me hold here in front of a piece of notebook paper is a crystal of the mineral calcite. It has the property that it splits light according to its polarization, which is why you're seeing two different copies of the notebook lines through it. If I hold up a piece of polarizer in front of it and rotate through, you can first see one line and then the other. So it turns out that the two planes of polarization are at right angles to each other. All right, so how much light gets through? Well, remember, what we're interested in is what's transmitted through. Now, the intensity is proportional to the electric field strength squared. And we remember that our electric field is going as the sine, so this is going as sine squared. In the last video, we saw that the average value of sine squared is 1/2. So if our initially unpolarized light, so we'll say that this has intensity I naught here. It has intensity I naught. What will pass through is intensity I. And because we average over every possible angle, because we've got every possible polarization axis here, this will go as the average value of E squared. So we get that the intensity that we observe is 1/2 of the initial intensity, because the average value of sine squared is 1/2. This gets called the 1/2 rule, cleverly enough. So if you have initially unpolarized light over here, that ends up polarized over here. It ends up polarized, and the intensity of light gets dropped by 1/2. Now, what if the light is already polarized? So if the light is already polarized, let's go and look look through a polarizer, and we'll say that this is our polarization axis. So if the incident light coming in is polarized like this, so we'll say this is the light coming in, what will get transmitted through will be that bit parallel to the polarization axis, because the bit perpendicular will get absorbed by the polymers. So we'll say that this is E naught, and then we can project back like so. This bit here will be, let's do it in a different color just to make it a little more clear. This bit here will be our new polarized light. So every time you pass through a polarizer, you change the direction of the polarized light to match the polarization axis. Now, since the intensity goes as the square of the electric field strength, this bit right here, if this angle here is theta, then this new electric field strength will be the old one times the cosine of theta. So squaring, that's going to give us that our new intensity is equal to our incident intensity times the cosine squared of theta. So what if you have multiple polarizers? Well, with the very first polarizer, you have to ask yourself if the light was already polarized or not. If not, you use the 1/2 rule. If it is, then we go right ahead to using, this is known as Malus's Law, right away. For subsequent polarizers, what you do is you figure out the angle between each subsequent polarizer. And then you apply Malus's Law, passing through each polarizer in succession. So I'm going to go ahead and show you another video clip here. Until here, when they are 90 degrees apart and basically no light is passing through. Now, what I would like you to think about for just a quick pause and ponder moment here is what would happen if I stick in a third polarizer in between the first two, angled 45 degrees with respect to both axes. So right now you've got one polarizer is horizontal, the other is vertical. I want to insert a third one in the middle at 45 degrees between the two. All right. What do you know? It passes some light through. What's going on with that? All right, so why was it that light passed through in the second case? So the deal was when the light passed through the first polarizer like so, I made it vertically polarized, I believe. We had unpolarized light over here. And then when we left, it was now polarized like so. The second polarizer was tilted at 45 degrees. So when the light exited it, that light was also tilted at 45 degrees. And then finally, for the last polarizer, it was horizontal and that light exited out horizontally. So here, the intensity here was I0 initially unpolarized. The intensity here was 1/2 I0 by Malus's Law. Now the intensity here is going to be 1/2, and by the 1/2 rule. Here, by Malus's Law, the intensity is going to be what it was before, which what it was before was now 1/2 I0 times the cosine squared of 45 degrees, which turns out to be 1/2. So we're down to 1/4 I0. And then here, it's the same deal. We take that exact same light. Now we take the light that exited here, so now at 1/4 of initial intensity. And then we have cosine squared 45 again, which is another 1/2, to end up with 1/8 I0. So it wasn't complete extinction. Some light was still indeed going through. And believe it or not, if you stack even more polarizers in between, making the angles thinner and thinner and thinner, more and more and more of the light will go through. And all you end up doing is twisting the plane of polarization of the light. And this happens a lot with certain molecules. They have what are called, they're twisted, and they have what's known as a chirality. And people will refer to a molecule as being right or left-handed, depending on which way the light gets twisted as it travels along the molecule. Alrighty, so in the next set of videos, we are going to take the fact that the Maxwell equations predicted that the speed of light is 1/epsilon naught mu naught, observe that that was due to that that does not say who the observer is, and use the demand that everybody has to have the same speed of light to start developing Einstein's theory of special relativity. See you over there.